Okay, so if we're looking at number 3, we have a 15-meter long plane is inclined at 30 degrees. If the coefficient of friction is 0.426, what force is required to move a 40 kilogram mass from rest to the bottom of the plane, at the bottom of the plane to the top of the plane with a final velocity of 8 meters per second? So first thing I did was I drew that out. 30-degree plane, 15-meter plank, 40 kilogram mass. I even put in VI is 0 and VF is 8 meters per second. I then worked out everything else that I possibly could, starting with, well, I know gravity. The force of gravity is just mass times the acceleration due to gravity. So that's 40 times 9.8. Got 392 newtons. I then know that if it's 30-degree angle for the plane, 30-degree angle for breaking up my vectors, and I broke it down into its vector components. Hopefully you already know how to do that by this point. Some of these I rounded. That one didn't round. And once I have that, I can then figure out the normal force because it's perpendicular. It's going to be equal in magnitude to the gravitational force in the y direction. And so I changed it. That's a negative, by the way. I don't think I put a negative there. I guess I should. So negative 196. All right. And after I have the normal force, since they gave me the coefficient of friction, I can figure out the frictional force by multiplying the normal force times the coefficient of friction. And I got that. And yes, that too should have been a negative, mostly because, yeah, it's going down. All right, so after I have all of that worked out, I now have everything I need to start solving the problem. Because if you're looking at this, you have an initial velocity, a final velocity, a displacement, and you're looking for an acceleration so you can figure out the net force, right? In fact, if we look down just a little bit, you can see that the net force is equal to mass times the total acceleration. It's also equal all the sum of the forces. Well, the force we're looking for will be the one that's pushing it up there, but it's hard to figure out unless we know what that net force is. And to do the net force, we can go ahead and figure out the acceleration. How are we going to do that? You guessed it, kinematics, my friends. Let's see if I can still move this. There we go. All right. So those same kinematics we used before are going to come in again. I'm using the fourth kinematic equation. That's final velocity squared is equal to initial velocity squared plus 2 times acceleration times the displacement. But I'm going to simplify first by getting rid of anything that's a zero value. We know our initial velocity was, so it's canceled out. We know our initial displacement is because we're going to make the bottom of the ramp 0. Because of that, I can rewrite the equation super simple, solve for A, and I get that the velocity final squared divided by 2 times the displacement final is going to be equal to my acceleration. Plug in those values, you should get an acceleration of about 2.133 infinite meters per second squared. Now that I have that acceleration, that's going to be the acceleration that affects the overall mass and the overall net force. Because of that, I should then be able to move this back around. Let's see if I can get it down here. And I can start to plug in things into that net force. So now I have my total mass, 40 kilograms. My acceleration, just solve for that. Multiply those by each other. I now know that the net force is 85.33 newtons. Since I now know the net force, I can start to look at the sum of forces, because if I look back at that, we can see that the normal force is going to balance out that force of gravity in the y, so we don't need to worry about our y. By the way, with all of this, we should have tilted our axis at some point in time. So there's our positive x, this is our positive y. Okay, so all we now have are forces in the x, but we have several of them. We have the frictional force that is in the same direction as a gravitational force pulling it down the ramp. But if it's going up the ramp, that means there has to be an applied force that's going up the ramp. So that net force told us that the net force is up the ramp, but we have to deal with both of those in the negative direction. So that brings us back to rewriting our net force equation with the sum of forces as the applied force plus the kinetic or frictional force plus the force of gravity has to equal that net force. Since we don't know that one, we solve it for applied force, and we have that the net force minus friction minus gravitational force will equal the applied force. But notice these are negatives, and that's negative values, so it's really adding all of them together. Place all of them in, add it up. You're going to get that applied force is 425.95 newtons. And that's your answer. Okay, so in problem number 4, we have a person pushes on the handle of a lawnmower with a force of 280 newtons. If the handle makes a 40-degree angle with the ground, calculate the coefficient of friction if the lawnmower weighs 350 newtons and is moving at constant velocity. Woohoo! Constant velocity. We know that that means there's no acceleration, meaning the net force is 0. Okay, so first thing I do is I go ahead and figure out that applied force on the handle of a lawnmower is going to be down at an angle from the ground like this. If you think about the shape of a lawnmower, that should make sense at the angle that it's in. I can then break that into its vector components using my sine and cosine feature. I then also know from just the problem, I don't even have to calculate it. I know how much the gravitational force is because they just call it a weight. Weight on Earth is the gravitational force, right? I also know that my normal force is going to be the sum of all the forces down pushing up because the lawnmower is not going through the ground. So in this case, I have part of my applied force going down and part of gravity going down, and so I have to add those together until I get a great big normal force. That only leaves the applied force pushing it along and the frictional force that we now know has to be equal to that applied force because of the constant velocity. So since I say those magnitudes are equal but opposite, I can then go ahead and say that that frictional force is going to be 214.5 newtons. Well, negative that, but it's not going to matter too much with the way that we're doing things because we're going for a ratio anyway. Meaning we're going to use that the frictional force is equal to the normal force times the coefficient of friction. All right, so now that we have all that info, we can pretty much come down here and plug all of that in. Once again, I rewrite that my frictional force is equal to the normal force times coefficient of friction. Solve it for coefficient of friction. I get that the frictional force divided by normal force. Plug in those values. Again, I'm not worried with up and down because this is a ratio value, so we want a positive value. And so we get that this is 0.405. Remember, coefficient of friction has no units, and that is our final answer. That seems like the simplest one yet.